talked briefly at the beginning of the year about rational functions. We mostly talked about what they were and how to add them, subtract them, multiply and divide. That's what we did with rational functions at the beginning of the year. We're going to start graphing them and using them for things. Just a quick review. Remember, a rational function is basically the function that has some sort of polynomial on top and a polynomial on bottom. Okay? So it's like x squared plus 2x plus 3 over x squared minus 6x plus 17, something like that. The problem on top, the problem on bottom. Okay? Okay, so let me ask you some questions about this particular rational function. Well, not yet. Let me go back to algebra 1. What is domain of a function? Yes, it's your x values. Right. X values, your input. Yeah, that's domain. And what's range? Okay, so if the domain is the x values, the range is the y values. If I'm looking at this particular problem right here, and there's a problem on top and a problem on bottom. Are there things for this particular problem that can't be in the domain? I can put 0 in, because if I put 0 in, then it's going to be 2 over 5. So I can put 0 in. But you're on the right track. It can't be 5 or 1, because what happens if it's 5 or 1? Right. It's not that I can't have 0 in it, it's that I can't have 0 as my value on the bottom. Because, can we divide by 0? No, division by 0 is undefined. Okay? So this function right here is undefined at any place that this equals 0. Well, where does it equal 0? Okay, well, what multiplies to equal 5 but adds to equal negative 6? So, my domain for this particular problem, my input, my x values, what I'm putting into the problem, is any number except 5 and 1. Because what happens if I put 5 into this problem? Right, see. 5 squared minus 6 times 5 plus 5. What's 5 squared? What's 25 minus 30? And what's negative 5 plus 5? Right. The same thing will happen if we put 1 in. Okay? You get 0. So 5 and 1 cannot go into this problem. When I'm looking at the domain of this problem, I can put any number I want to in, except 5 and 1. They're undefined. Okay? Now, I can put 0 into the problem. Okay? That causes a lot of confusion for some people. 0 can go into the problem. 0 can come out of the problem. I cannot have just the bottom equaling 0. That's not a thing, okay? That's not allowed. Just the bottom equaling 0. Alright? Let's talk about domain for a second. Actually, I want to... So on number 1, that was pretty easy. What can x not be? 0. It's 1 over x, so x can't be 0, right? Okay. Alright, number 2.
3.
Why 3?
Because 3 minus 3 is 0.
Right, if I put 3 in for x, so my domain I could say it's all real numbers except 3. Okay. I could write it on, let's see, negative infinity to 3, and then 3 to infinity. I could write it like that. I could write x such that no, the other way. I like that. This is my favorite. Alright. What about the next one? Number 3. Is there anything that x can't be? Well, if I put negative 1 in, this is x squared plus 1. If I put in negative 1, what happens to it? It becomes positive, right? So is there anything x can't be? It's all real numbers, right? All real numbers. Because I'm squaring it right away, and then adding 1, I can even put 0 in there, right? Because what happens? 0 squared is 0, and then plus 1, 1. So here's another way. Let's actually solve for x. X squared plus 1 equals 0. So I'm going to subtract 1. X squared equals negative 1. X equals plus or minus I. What kind of number is that? Imaginary. We're talking real numbers here. So is there any real number that x can't be? No, right there. We just proved it algebraically. So for number 3, it can be all real numbers. How about number 4? Alright, anything but plus or minus 5. So you've got x squared minus 25. You can factor that or you can just solve it. So all real numbers except 5 and negative 5. Alright, now number 5 starts getting a little bit ugly. 5 you have to factor. By the way, if you don't know how to factor still, you have to learn, because this section is, the first step is factoring. On every problem, the first step is factoring. So if you still can't factor, get on Khan Academy, Google factoring, instructional videos, whatever, learn to factor. You have to be able to factor. Alright, so number 5, we're looking for the zeros of the denominator. Zeros of the denominator. That's what we're looking for. So what are two numbers that multiply to equal 36 and add to be negative 15? 3 and 12? Negative 3 and negative 12? that, and I have 2x minus 3. I go to negative 6, and I have 2x minus 3. So it's x minus 6 and 2x minus 3. So for number 5, it would be all real numbers except 6 and 3 over 2. Because what happens if I put 6 in right there? What's the answer? 0. Can't have 0 in the denominator. If I put 3 over 2 in right there, you get 0. Can't have that in the denominator. Alright, I'm going to give you a couple minutes to try 6, 7, and 8 by yourself. Completely by yourself. And then we're going to start talking about asymptotes. Yes. Alright, number 6. Number 6, all real numbers except for what? 3/4 and 6. Yes, all real numbers except 3/4 and 6. Alright, what about 7? 0, -2, and 6. Yes. 0, -2, and 6. Don't forget, they all share an x, so you can factor that one out right away. So 0, -2, and 6. And how about number 8? Alright, number 8 is all real numbers except plus or minus the square root of 5. Because that's what happens when I solve for 0. And that's a real number. It's irrational, but it's real, okay? So I can put in any real number I want except for the square root of 5. Plus or minus the square root of 5. Any questions about domain? No? Okay. These things in the domain that x can't be, they turn into discontinuities in the graph, okay? They turn into, like, a polynomial is a polynomial because it has a smooth graph. You never have to pick up your pencil, okay? You can graph it if it's a curve, or it's a smooth curve. You can graph it beautifully. Even trig functions, some of them, they repeat over and over again. But you never have to pick up your pencil, okay? But when we start having things in the denominator that x can't be, it's not smooth anymore. Because x can't be that number. You can't put it there, okay? So we get these crazy things, these rational functions, and some of them will look like this. Another one down here. Sometimes they look beautiful. You're like, yes, that's a polynomial. Because it has this nice graph, and then it goes, wait a minute, I got a hole right there. I can't do that. X can't be that number, so there's a hole in the graph. Okay, so you have these discontinuities here. These discontinuities turn into asymptotes or holes in the graph. Okay? And that's what we're going to start talking about now, are the asymptotes.
That's teaching.
Alright, so let's see if we can start finding. So a vertical asymptote and this is a very not math definition, okay? Not math definition. But it's basically what x can't be. Okay, it's what x can't be. And I'm going to put it in parentheses here. that didn't cancel out. We're going to talk about that canceling out business in just a minute. But you need to know that vertical asymptotes are born from those numbers that x can't be. Okay, show me which way does x go? Which way does x go on the graph? Okay, it goes side to side, right? So if I have a graph and let's say x can't be 2. Where can x not be 2? At 2. What about right here? Can x, it's all the way, like this whole line right here of numbers are completely out because x can't be 2. X cannot be 2. See, this is x is 2 right here, x is 2 right here, x is 2 right there down on the floor, and x is 2 all the way up there at the ceiling. That whole line is out. If x can't be 2, you got to take the whole thing out. That's how we get this vertical, see, it's up and down, vertical asymptote, because this entire line of 2's are knocked out. And we put a little dashed line there to show, hey, x can't be anything along this line, okay? So that's what we're looking at when we say it's a vertical asymptote. It's what x can't be. We put a line there to say, hey, these are the things that x cannot be. And usually, I will probably never write this again. It'll be VA from now on, okay? That's what it is. So where does the VA, where does that vertical asymptote come from? How do we determine what x can't be? When we just did domain on 1 through 8, where did we go to find out what x can't be? Back to the denominator. Back to the denominator. And then we solved the factors. We basically found the x-intercepts. Basically, we found the x-intercepts of the denominator. Okay? Alright, so let's find some vertical asymptotes. We're not going to do anything with them just yet. We're just going to find them. Alright, so where are the vertical asymptotes for this function? Where are the vertical asymptotes for this function? Alright, what is this factor here? X plus 2? So we have vertical asymptotes at x equals 3 and x equals negative 2. If we were to graph this, we would have to put a line here to let people know, hey, x can't be 3. And we put a little dashed line here to let people know x can't be 2. Right, those, they can't cross. Rational functions don't cross or touch vertical asymptote. Okay? They get forever infinitely closer to it. They don't touch them and they don't cross them. But forever and ever and ever and ever get closer. But they never touch it. Okay? Ever. Like when you're sitting in the back seat with your little brother and he's going, I'm not touching you, I'm not touching you, I'm not touching you, I'm not touching you. That's what they're doing. That's what a function does. It's not touching it forever. It will never cross, it won't touch it. Okay? That's a vertical asymptote. But we will do a hole in the graph. Alright, so we talked about that didn't cancel out. Okay? If it cancels out, if you factor the top and you factor the bottom, and something cancels out, it's not an asymptote, but it is a discontinuity. It's just a hole in the graph. Okay? So let's say, here, I'll use that last one. What was it? X squared. Alright, so on this one, the top we know factors to x minus 3, x plus 2. We just did that. The bottom is going to factor to x minus 3, x minus 3. It's a bad example because it still has one. Let's flip these. Alright, so we said in the last problem that we had an asymptote at 3 and at negative 2. See how this cancels out? There's an x minus 3 on top and an x minus 3 on bottom. That's not going to be an asymptote. There's just a hole in the graph. So when we graph this one, whatever it looks like, as we're going along, when we hit 3, whoop, there's 3. I'm just going to put a hole in the graph and then keep going with whatever it would look like. Okay? When it cancels out, hole in the graph comes from factors that cancel. It's still a discontinuity. Okay? It's still a discontinuity. It's just not an asymptote. Alright, look on this page that you have.